This is an example of Bayes' theorem. With Bayes' theorem, with this problem, we're going to start with some initial guesses as to whether students have chickenpox or not, and then we're going to update those probabilities based upon test results. We're not going to show this example with the Bayes' theorem equation because I think it is more intuitive to see Bayes' theorem as a table where the probabilities get updated and ignore the Bayes' theorem equation, which uses the likelihood and the prior. So here in this example, we have students and we know that 20% of them have chickenpox. That's 20% of them have chickenpox, which means that 80% of them don't have chickenpox. We also know that we have a test for chickenpox, but that test is sometimes right and it's sometimes wrong. If they actually have chickenpox, then 70% of the time it will return yes, they have chickenpox, but 20% of the time it will return no. So that's a true positive and a false negative rate. And if they don't have chickenpox, which is 80% of the kids, then 75% of the time it will return no, and 25% of the time it will return yes. That's a true negative and a false positive rate. So there are four possibilities. They either have chickenpox and get a yes, they have chickenpox and get a no from the test, they don't have chickenpox and get a no, or they don't have chickenpox and get a yes. With this two possible things, we can make a probability table. The probability table shows us that these are the odds for any given child of the four possible states. Because 20% of the kids have chickenpox, and 70% of the time a chickenpox students will get a yes, that means 14% of the kids will both have chickenpox and get a yes. And 6% of the kids will have chickenpox and get a no. Likewise, 20% of the kids will not have chickenpox, which is because there's 80% of the kids don't have chickenpox, multiplied by 25% false positive rate. So 20% of the children will not have chickenpox but get a yes, and 60% of the children will not have chickenpox and get a no. So far, we haven't used Bayes' theorem. This is a probability table that you could make without using Bayes' theorem at all. This is just the starting state. We use Bayes' theorem when we roll in some results to change our probabilities. Here what we're going to roll in is the results of a test. A test is either going to come back positive or negative, and we're going to use that to update our possible outcomes. In our starting state, we have four possible outcomes, but after we do the test, we split those four possible outcomes into pairs of two outcomes. We either get a test that's positive, in which case we pair off the two with the true positive and the false positive, or we get a test that's negative, in which we pair off the true negative with the false negative. And this means that our probabilities get updated. So here our odds of having if we get a positive test, our odds of actually having chickenpox become 41%, which means that a positive test changed our total odds of having chickenpox from 20% to 41%. But we still have a 58% chance of not having chickenpox. A negative test changes our odds of not having chickenpox from 80% to about 91%. If we look at that in a table, what's happened is we start with these odds sum up to 100%. But afterwards, we are only keeping one row. So if we get a positive test, what's happening is we are keeping only this row. So if we get a positive test, we discard any results that are associated with a negative test. Effectively, what we've done, if we get a positive test, we go down this path and we discard these results. That means that our total odds now, if we sum them up, are only 34%. There's only a 34% chance of getting a positive test. But after we get the positive test, then that's already happened, so there's a 100% chance that this happened. So we need to scale our results to make these sum to 100%. So now we have, if we scale these up, that means that our odds of having chickenpox and getting a positive after we have a positive test are 41%. And our odds of not having chickenpox after a positive test are 58%, 59%. Likewise, if we had gotten a negative test, we would effectively just keep this row. And then we would scale these results up to sum to 100%. So here it's 61%, 66%, and we need to scale these up to sum to 100%. That would scale up to about 9.1% and about 91%. So I think this is a more intuitive way to think about Bayes' theorem. Instead of thinking about the priors and the likelihoods, it's you're making a probability table with all of the possible initial states and all of the possible outcomes. And then you're just keeping the row that's associated with whatever outcome you get. We still don't know our initial state exactly. Even after a positive test, we still don't know if we have chickenpox or not. But it has changed the probability. Or after a negative test, we think now we don't have chickenpox. We think 91%, but we don't know this for sure. But this has given us more information. Maybe we can go do another couple tests. Maybe we're confident enough. But this is how you can use Bayes' theorem to update estimated probabilities as you get more information.